Our next speaker is Dr. Sameh Abdullah from King Abdullah University of Science and Technology in Saudi Arabia. So Sameh is going to talk about sustainable geospatial climate and weather modeling on modern Manycore systems. So Sameh is a OSU grad, so I happen to study here at the same time as he was. So post-graduation, he joined KAUST, and currently he serves as a research scientist at the Extremes Computing Research Center at KAUST. So let's welcome Sameh.
So I'm not sure it's stuck like that. So. How it works. Yes. Hi, everyone. My name is Sameh Abdulah. I'm working as a research scientist at the Extreme Computing Research Center at KAUST. Thank you, Dr. Panda and Harry, for inviting me for giving a talk about our recent work. Actually, it's a good thing that this work is recent, and we just submitted the paper to archive 3 days ago, so this is the first presentation about this. We will have this again at SC if you will attend SC, so you will not miss something at SC after this presentation. So this work actually has been nominated as a Gordon Bell finalist in the climate track this year at SC, so I'm very happy to present this today for the people here. So this work is a collaboration with a lot of co-authors, as you can see. Some people from HPC side, from KAUST, and also from University of Tennessee. And we have some people from the science part, which is climate simulation and emulation from Manycore, and also from the stat department at KAUST, and also at the University of Notre Dame. So let me give some introduction about our problem and how we can solve it. All of you know about this climate change thing and the problem that we have about a long-term shift of the temperature worldwide. And for example, you can see that just this year, in 1 year, you can see a change on the temperature by more than 1.5 Celsius, and this is a big problem related to climate change, and this the things that make problems on different parts of the world related to earthquake and storms and floods. And for that, the earth scientist people are trying to understand what's going on and what's the expected change in the future. And they are doing this using what we call climate models. So they have their own way to use the physics and the mathematics to build a model to simulate what's going on the now and what will happen in the future based on historical data they have, and they call this climate models. The problem of these climate models that are sophisticated, it's very complex and need a lot of computing power, and to understand what's going on, you need to generate a lot of data or simulate a lot of data using these models. The other way around to avoid the climate models is to use climate emulators. And these climate emulators are a little bit light in computing and to be generated compared to climate simulation, so that you can simulate some data set and then use the emulator to emulate more data sets looks like the same data that can come from the simulation. And those emulators are used now by the earth science people so that they can reduce the computation needed for the climate models. So the question here that we need to solve, we saw this in the literature. We saw the earth science people are trying to use the emulator, but we didn't see a way to do emulator in large scale. So exascale emulators where you can generate a lot of data sets and at the same time mimic large sets of data sets generated from these climate models. So first, let's introduce climate models to understand it more. As I said, it's a way to use the physics and the math to understand or to generate data set to understand what's going on in the climate and weather data. Those models are very complicated. I think most of you heard about BDEs. So they are using BDEs, which need a lot of computing power, and there is a lot of research just to improve the computation or the computing techniques and methods for the BDEs. So the climate scientists relies mainly on those climate models. And the main problem here that we don't have just one climate model. Each research group or each climate institute in the world has its own climate models. So 3, 4, 10 climate models, and they are using those climate models to generate a lot of data sets. Then after generating, they are keeping this for several years or many years just to study the data set that they have. So because of that, there is some projects related to the earth science people to just collect the data sets coming from different models, from different institutes, from different research groups, and put it on one place. Then the earth scientists can use it to make more experiments. And one of those projects called CM project, which has different versions of data sets collected from different institutes, and it's available online, so the scientists can go there, download the data sets, and deal with it. The problem of such a project that each institute, each climate weather institute, need to generate data set to participate with those international collaboration and give them some data sets. Generating the data set from the model, it consumes computing power, it consumes space. So this is some examples here. For example, Manycore, to simulate based on 37K years, they consume about 190 million CPU core hours just to generate 2 petabytes of data to give it to SIMP6. This is the last version of this group of data sets. GIS from NASA, they contribute to SIMP6 by 147 terabytes, and they consume around 100 million core hours to generate the data set, and others and others and others. So you have one problem that each institute need a lot of computing power to generate the data set. Then I collected the data set. I need to take all the data sets, store it somewhere so anyone can access it and do some studying on that. So we have a problem related to the computing power and related to the storage. That said, no, we have also a problem related to the cost of saving those data. This is some example, and this is the good thing about this project. We have people from different institutes, and they give us some information that's very hard to get it from papers or even online or from any source. So for example, the Manycore people told us, in average, each terabyte, they keep it for 1 year on their storage, it costs them about $45. And they need to keep this data for several years, for many years, and this is a big problem. So we need to solve 3 problems related to the computing power needed for those models to be generated, the storage, and also related to the cost of this storage. That's it. No, actually, those scientists are not care about those 3 things and start to create more data set with higher resolution than what we have now. For example, those simulations can have data sets up to 100 kilometer resolution over the world, over the globe. They need to reach to ultra high resolution, which is 1 kilometer, which means more data, which means more computing power, more storage, and other things. And there is some examples, I will go fast on this, but there is some examples of projects just care about generating very high resolution data that will need storage and computing power. So this is why they start to use climate emulator. Climate emulator try to get more simple way to generate the data set and also can replace those data set with a set of parameters, so that when you need the data, you can go back to the parameters and generate the data that you want. So you don't need to store your data to a hard disk for 5 and 10 years. No, just store those statistical parameters and reuse them later when you need a data set related to, for example, to 2030. Okay, so I need it now, so let's go and generate it very fast and very accurate. Those emulators actually depend on statistical model and a set of statistical parameters. So you don't need to store even 0.1% of the data set that come from the climate simulation. You just need very small storage space to store your statistical parameter. So where is the contribution that we have on this study? So our contribution is we developed for the first time the first exascale climate emulator ever. We rely on the state-of-the-art work related to the climate emulator by using what called SHT, spherical transformation, that used to emulate the simulated data. So this is an example of one animation we put in our paper related to the data coming from the climate model and the data that we simulate, we emulate actually at the same day. So we used here about 83 years to get the animation on the right. This is an hourly data or 2-hour data that show that we are very close to the simulated data. Actually, the point here is not to generate the same data, but the same behavior of the data, and this is how the climate models works. So we developed the first exascale emulator which is 245K higher than the existing emulators on space and time, okay? So we are achieving 28 times more spatial and 8,760 times greater in time resolution. We used hourly data on 83 years and also over the whole world, okay? We reach to emulate climate simulation with up to 3.5 kilometers. As I said, what exists today is 100 kilometers. With this exascale emulator, we reach to 3.5 kilometers. And actually, once we publish the paper, the first messages we receive is from climate people about this 3.5 kilometers. So we didn't receive anything from the HPC people or from supercomputer about the performance. Just they ask about this 3.5 because they think, okay, this is too much. How did you get that? We are able in this work to do emulation for 83 years, from 35 to 83 years on hourly data, not daily. Okay, so you can multiply how many days, how many hours, and you can see how much data we used for the training. We used the SHT technique, which is the new technique, to do this emulation thing. We train our model using 477 billion data points. Those are all the points related to the hourly data for the 83 years. This is related to the science. This is good. What about HPC? What about parallel processing? Actually, we optimized our code, which depend mainly on linear solver, on Cholesky factorization and circ operation, on 4 different supercomputer systems. On Frontier, which is #1 on the top 500 list, and we are able to reach almost 1 exaflop using mixed precision technique to solve this linear solver. We reach to 0.739 with ALPS, which is the new system on Switzerland that has the Grace Hopper supership, and on Leonardo in Italy, 0.243 and 0.37 on Sameh. So our code can run everywhere. We run it on 4 different systems with 4 different GPUs with a very good performance compared to the peak performance, and we are also able to scale it on Frontier to almost full the system. Also from the HPC perspective, our scalability the strong and weak scalability of our system, shows a good performance on Summit, which is the main system we use to estimate or to check our scalability. Okay? I will not go in details because actually all the things here related to the science, but I will simplify it for you here. So the main thing here that you have a data set. The data set is a temperature data set that represented on longitude and latitude. So on longitude 10 and latitude 10, you have temperature 32. And then you can go further. You have over the globe, over the world, we have 1,440 longitude and you have 720 latitudes. So this is the whole spatial points you have in the world. That's it for now. This is the climate simulation can reach to this point. Then you have the time slot. So you have this temperature on this place on 83 years hourly data. What we are doing with our emulator that we are taking as much as we can. As I said, the maximum that can we reach with our emulator is 83 years. You can take all this data, convert it using SHT from the spatial domain to the spectral domain. Once you do this movement to spectral domain, you can understand what's going on related to the frequency of the behavior of the data. Once you understand this, you are generating what we call the covariance matrix, which is a matrix that represents the correlation between different measurements we have on different spatial location through the time. Once I have this covariance matrix, I can get from it a set of parameters that can be used later to generate any data set that we need to mimic the original data set. This is the science part. This is the algorithm. If you look to the paper, you will find 9 stages with linear solver everywhere, with matrix operation, with circ, with Chwalowski, but this is the conclusion of the algorithm, as I said. So I will not go in detail here, but let's go to the complexity of this algorithm. We have 3 main parts of this algorithm. The transformation from the spatial domain to the spectral domain, this is one. The second is to generate the covariance matrix with 2 operations, circ operation and Chwalowski factorization. The complexity of doing this conversion is L squared plus T, where L is the number of spatial locations that you have, and T is the number of time slots you have. With the circ operation, we have L to the power of 4 plus T. And with Chwalowski, you have L to the power of 6. This is the overall complexity. And we found that the bottleneck of this algorithm is to apply an inverse operation on the covariance matrix, which is Chwalowski factorization. So we focused on Chwalowski factorization to see how to solve this on GPU system with high performance and also with integrating mixed precision technique to have this solution. This graph, you can also find it on the paper, show what's the current literature on the climate emulators and where our work is. As you can see on the green part, this is the literature. So the people can do emulator up to 100 kilometers. And you can see all the side on the right, this is where we are. We have 4 points to reach to this 3.125 kilometer resolution. And this is how large we can solve. And the good thing here that if you look to the dashed lines, this is show what if we use approximation? What's the complexity of the algorithm? And the solid line is related to the dense solution. So we are doing exact emulation. And this is what we are doing in this paper. If we can relax the algorithm a little bit and start to use approximation method, actually we can go higher resolution than what we have here. So those are the 9 steps that we have on the algorithm, but let me go directly to the HPC innovation that we have here. So the main problem here that all these operations is matrix operation. You have a very big matrix, which is the covariance matrix, and this covariance matrix, you need to do some operation on it. So we are using at ECRC, and actually this is coming from Jack Dungara from Tennessee, what the algorithms called tile-based algorithm, where you can split your matrix to small parts, and then using the available processing units, even its CPU, GPU, even FPGA, you can use any of them to solve just one tile. This is what you can see here on the left. So if I am doing in a simple algorithm, if I'm doing gem operation, matrix operation, I can easily take one tile from the first matrix, multiply it with one tile on the second matrix, and put it on the third tile on the final matrix. Then I can use all my resources. We are doing this and depending on a runtime system called Parsec from the University of Tennessee. That runtime system can help you to schedule those tasks on the available processing unit on any system, regardless of the architecture that you have. So it's very optimized on different architecture that's available today. And let me tell you one secret about ALPS. Do you know about ALPS supercomputer? How many of you know about it? Yeah. So ALPS is the new system with Grace Hopper GPUs. And we didn't have an access before to a system with this large with Grace Hopper. And we got an access 2 days before the submission. And we apply our code there directly, and we got very high performance, okay? So using or relying on the runtime system can help you actually to get the performance on different architecture without changing your code. Sometimes there is a problem, but sometimes it works very good. So those tile algorithm at KAUST, we had an idea. Since we already split the matrix to parts here, why not to do the operation per tile and choose a specific precision for each tile to do the operation? And we rely on the science where we know that the tiles, I don't know if we have pointer here, right? Okay. So we know that the tiles on the off diagonal of the matrix very far, it's not that important on the science. So it doesn't have big information related to the science. So we decided to make those tiles with a half precision operation. They are not important. And keep the double precision operation just for the gray one, for the close to the diagonal. Then actually in 2021, Nick Hayam had an idea of, depending on the norm of the tiles, to decide which tile to be represented in which precision. At the end, the conclusion on this, you can distribute the precision on your matrix and do your operation, and at the end, you are getting the accuracy you are looking for. So the best performance ever with the same accuracy if you use double precision. And this is what we applied here on this application. So why mixed precision? Why it's important? I think all of you know with, this is just examples from NVIDIA GPUs, that the speed up that they are providing using the tensor core on single and half precision can reach up to 30 and 32x speed up compared to double precision. And at the same time, we are not losing a big accuracy compared to existing approximation method like low rank or other methods related to data sparsity on the matrix. So this is how our algorithm works. We rely on Parsec, the runtime system. We are representing our algorithm, the linear solver, Cholesky, Cirque, GEM, as a DAG diagram where we are showing the operations and showing the dependencies. We just give this to the runtime system. Okay, we need to do this operation and take care. We have those kinds of dependencies. Then the Parsec take care of distributing the tasks here to different processing units and take care of the dependencies between the tasks. Once we have the algorithm and we have the DAG diagram, then we can use the underlying hardware in a more efficient way and can scale as good as we can. Okay, we have some restrictions here, but I'm talking about the ideal case. So let me show you some performance results, but first let me give you some consideration about the data set that we use here. We depend on our experiments here on a temperature data set, again, over the whole world, and we depend on spatial temporal data, not just spatial data. These considerations are very important because you may find some work that can reach resolution up to 1 kilometer, okay? But they are using this on the area on the US, for example, not on the whole world. So I'm talking about the whole world. We are talking about spatiotemporal data. we are using data set called ERA5 data set. This is a climate model simulated data set, and we use it for 83 years to train our emulator. And actually, this is one thing. We tried to find existing real data set coming from the simulation, and we found that they cannot get resolutions more than 0.25, okay, which is about 100 kilometers. We need our emulator to emulate more than this. So this is why we did here, this is some parameters related to the algorithm, but we did the data interpolation. So we tried to take the simulation, interpolate data to increase the resolution, just to see if our emulation looks the same as the simulated data or not. And why we did that? First, to show the scalability and the performance of our emulator. Second, to keep our approach aligned with the advanced in climate modeling. So our emulator can work with existing simulation and also with the future simulation, which not yet reached to the same resolution. This is some accuracy results using different precision if we apply fully double precision or fully half precision. We are using DP there because usually we are making the diagonal of the matrix double to be sure that the matrix stay positive definite matrix. And as you can see here, that our emulation looks like the simulation part. You will find some changes visually, but this is normal because we are not copying what's coming from the simulation. So these are the results that we got on the 4 systems related to the performance, related to the number of nodes that we had an access to give the best performance related to our application. Let me show you some graphs here related to the performance. This graph on Sameh on 12K V100 GPUs and show different precision with the same algorithm and how fast we are just by applying more precisions or less precision to the tiles that we have. And the speed up can reach to 5.2x from the double precision up to totally half precision. But again, as I said, this is depend on the application. Maybe the application will not accept to go to this very low precision. This is the scalability up to 200K GPUs on Sameh. This is the weak scalability where we are keeping the same workload on each GPU and increase the number of GPU. And you can see we have here very excellent scalability or weak scalability over the nodes. The most important thing is the strong scalability, where you start with a specific workload and keep it and increase the number of GPUs. And as you see, we didn't lose much of our scalability, and we can reach up to 72% with single and half precision. I like this graph because we spend a lot of time to see how we represent our results here, because we have just one runs on the 4 servers. You can see the points that we got on different supercomputers: Frontier 4 points, Alps 3 points, 1 on Sameh and 1 Leonardo, with different performance reached to up to 1 exaflops to this application. This is also something that at the end we realized that, okay, we got an access to 4 systems, but the good thing that the 4 system has 4 different GPUs types. We have V100, A100, GH200, the Grasshopper, and AMD on Frontier. So let's do this kind of comparison. So we use the same number of nodes on all the system, 1,024 nodes on the 4 system, which give you the number of GPU, 4,000 on Frontier, 4 on Alps, 4,000 in Leonardo, and 6,000 on Sameh because it has 6 GPU per node. And we show what's the largest matrix size that we are able to solve. Okay, let me go 1 second back. So you can see here the largest matrix size that we solve is 27 million by 27 million. Okay, and this is represent this 3.5 kilometer resolution. So we show here the largest matrix size that we can solve on those number of nodes. Then the performance. What I like here is the last row, which related to the performance per GPU for our application. Again, maybe this GPU is very good. I don't know if anyone here from AMD. This is good. We don't have. So I'm not sure about the AMD, maybe it's the best GPU ever, but for our application, we still can see that Grace Hopper and A100 getting better performance than AMD. AMD is better performance than V100 at Summit, okay? But this is related to our application. Maybe we will have problem with tuning our application on AMD, but this is the conclusion we got. So, summary of this work. Our objective is to create this exascale climate emulator that actually can mimic the simulation that we have now. The methodology we use the SHT methodology, which is the less computational complexity to any emulator, any existing emulator, with a resolution reached to 3.5 kilometer. The data we are using, we used hourly data, 318 billion to train our data, and 31 billion daily temperature data on 35 and 83 years. Our performance reached to up to 1 exaflops on Frontier, and the innovation is to use a mixed precision here with Parsec on different GPUs, on different system with a good scalability. And the impact that we think that this emulator can be used by the climate scientists to maybe reduce their storage need and the computation power they need for implementing those models. We have two references here, actually. Reference number 2 is the base, which is a set or some of the co-authors of the paper, prove everything theoretically to the stat community on the second paper. And the first paper, this is our GP paper, and it's still on archive. Thank you so much.
Any questions for Sameh, folks? Yes.
Thank you for your presentation. I'm wondering what kind of parallel programming model used in your climate simulation program?
What, sorry?
What kind of parallel programming model do you use in your climate simulation program?
What kind of climate model we use?
No, parallel programming model. Parallel programming model.
Oh, okay. So we rely on a runtime system called Parsec runtime system. The runtime system trying to make the parallelization process for you easier. So you can just CUDA using a sequential way and implement your CUDA kernel. You implement your CPU kernel, and the runtime system will run this on parallel based on MPI. Okay, so the runtime system itself is trying to abstract the parallel programming for you. So we are not using pure MPI or pure CUDA. No, just the CUDA and the kernels, which is sequential one, and the runtime system will play with that.
Any other questions?
So how much time is spent in communication in your workload typically? Is it mostly compute bound, the workload that you are describing?
Yeah, everything here is compute bound. And this is why I said everything dense. We don't have a sparse. We don't have an approximation. It's compute bound.
Okay.
Okay. And Parsec also is very good on hiding the communication when you have a compute bound application.
Okay.
Okay.
Any other thing? Any other questions for Sameh? Okay, so if not, let's give big thanks to.
Thank you.